Okay, let's take on a new topic in the area of gases, and these are going to be called the gas laws. They were a series of rules or relationships that were worked out over a number of centuries by several chemists. The first one is a fun quote by Torricelli. It's quite an interesting insight. It's very accurate that we are immersed at the bottom of a sea of elemental air. He is likening the gases that make up the atmosphere to one that is like a liquid. And in some ways, there are similar properties between them. Let's take a look at the basic properties composition of air. You'll notice it is made up mostly of nitrogen gas, followed by oxygen, and then there's argon and carbon dioxide, which is a rather large topic now because of the global climate changing that is going on due to the increased production of human activity. So it's mainly made up of nitrogen, and we will not work with air and its properties per se, but it's interesting to know the general composition that makes it up. What is the properties of all gases, including air, but what's the general property that all gases have? First of all, if you put a mixture of gases like air together, they will all naturally mix with each other. They'll evenly distribute themselves out. And the result is you get a homogeneous mixture together. You don't tend to see clumping of CO2 in the areas of Iceland, and you don't get a clumping of oxygen over the Pacific Ocean. Rather, everything evenly distributes itself. Gases are compressible, meaning you can change their volume by applying pressure to them. They have low densities. You don't build a building out of steel gas. You make it out of a steel is a solid. Gases simply have low density. And they assume the shape and the volume of the container, meaning they spread throughout the container. Think of a solid block of salt. You put it in a glass and the salt does not spread out and fill the glass, rather it maintains its own shape. That's not true for a gas itself. Gases are able to exert a pressure on a container. Now, gases are compressible. And that's an important idea. If you look on the left, you'll notice there's a piston system, and it's pushing down on a container of gas. And you can cause the volume to get smaller, although the overall amount of gas hasn't changed. Where is this extra space coming from? Well, when you compress a gas, you're causing the molecules to get closer together. And that is what allows you to compress a gas. You simply make the spacing less. Liquids and solids, the spacing is already so little between the atoms or molecules that make up the liquid or solid that when you push down, there's really no space, added space available to move the atoms or molecules into. And therefore, they do not get compressed, unlike the gases. Now, this idea about compressibility is illustrated nicely in what is called a J-tube for obvious reasons. And here you see that we have a gas on the left and we have mercury on the right. If you increase the amount of mercury on the right, the weight of the column of mercury gets greater and it pushes down through the J-tube and pushes on the gas itself, compressing it. So the J-tube is a nice illustration of the ability to compress the gas in a fixed area. Now, what kind of elements exist as a gas? Those that are in blue exist in its natural state at 25 degrees Celsius, 1 atmosphere. What is in turquoise or blue are things that would appear in a gaseous state. Take a look on the right, of course, is the noble gases, and they all assume a gaseous state when they are at this temperature. The diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, all assume a gaseous state. Bromine and iodine they are diatomics, Br2I2. But at this temperature and under these conditions, they actually assume a liquid condition, although they are diatomic as molecules in that liquid. What are some sample compounds that exist at 1 atmosphere and at 25 degrees Celsius? And they include NH3, that would be ammonia in the middle, carbon monoxide, carbon dioxide, sulfur dioxide, and these are all hydrogen cyanide. These are all molecules that exist in a gaseous state in these conditions of 1 atmosphere and 25 degrees Celsius. Now, gases exist at a certain temperature, and what is meant by temperature, as we know from the last unit, is it is the random motion of the molecules around. So temperature is actually the average kinetic energy of the molecules that are in a substance. They undergo random collision, and a thermometer is a measurement of that random kinetic energy or motion. To measure temperature, there are a number of units or systems that get used. The one here in the U.S. is Fahrenheit, and water freezes at 32 degrees Fahrenheit, and to 12 it's going to boil. Celsius is the one that is the scientific unit. It's the one that is universal, actually, except for the United States. And the water freezes at 0 and 100. And as we've started to talk about, there is a third one, which is Kelvin. And Kelvin has an absolute 0. It is a temperature that you cannot get less than, and they actually designate that as 0. Though in gas laws, we will be using the Kelvin increments, whereas all the other calculations in chemistry, we will use Celsius, and we never use the Fahrenheit. It's rather silly. So what is pressure? Obviously, pressure is when you have too many moles in a given volume. Yuck, 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 yuck. So what is pressure? Pressure is, in fact, the collision, the actual act of collision of a gaseous molecule on a surface. When that collision occurs, a force gets exerted onto that surface. And if you get enough of these gaseous molecules colliding with the surface, the sum effect is what we call a pressure on that surface. So pressure is the amount of force per given area. And what that means is if you take a gas and you spread the gas over a very large surface area, like a very large container, the overall effect is not much pressure because you do have force, but the force is being spread out over a very large container, so the pressure is less. Naturally, if you take a gas and compress it into a very, very small space, then the amount of collisions per surface is much more increased, and therefore the pressure increases. So pressure is force per area, and force is a mass times the acceleration. So in physics, we think of pressure as kilopascals, which is force over an area. As we'll see, chemistry tends not to use the kilopascals, but uses a different unit. But the definition of pressure is force per given area. Now, a man named Torricelli in the 1600s, a bit short-lived, as you might notice, he was the first one who figured out a way of actually measuring pressures of a gas. And what his realization was that atmosphere or gas from the atmosphere is exerting a weight, a pressure downwards on all surfaces. If you then take a vacuum tube and place mercury in that vacuum tube, what happens is the air pressure on the outside drives the mercury up into the tube. And that, in fact, the height that the mercury moves to is a measurement of the amount of atmospheric pressure A way of thinking about this is that the weight of the mercury column is equal to the weight of the air pushing down, or the pressure of the air pushing down. Those two will be equal to each other. And at sea level, the height of mercury will rise to 760 millimeters. Now that setup here, this system is referred to as a barometer. You'll notice it's a closed tube that is able to be pushed up by the air. There's another system called a manometer. And what a manometer does is it measures the pressure of a gas in a container. Notice it's not measuring the pressure of the atmosphere, but rather the pressure that's inside a closed container. One might imagine you could heat that gas up in that container, and that would change the pressure, and the result would be a change in the level of the mercury column. So a manometer allows you to monitor or measure the pressure of the gas in a closed container and not account for the pressure of the surrounding air. The closed tube here would measure it strictly as a temperature of the gas, whereas an open tube will start to account for the outside air. Now this is something we talked about, and this is what Torricelli was interested in. There is a column of air, well, there is air everywhere, but one might imagine a single column of air, and at the sea level we call that 1 atm, which is, by the way, 760 millimeters of mercury. Those are the same measurements. As you go higher up in the atmosphere, the column weighs less. There is less air above you. Therefore, there's not as much pressure. And at 4 miles, the pressure is half. At 10 miles, you're at a 0.2 atm. And the column of air extends up about 20 miles, and the pressure, of course, gets less and less because there's less air weighing down on you. Now, we can use this principle in the following manner. When you're taking a drink from the straw, you will notice that the cup has air pushing down on the surface of the liquid. When you draw air out of the straw, you lower the pressure inside the straw. Result, the outside pressure, the outside weight really, of the air pushing down becomes greater than the column of the liquid that's in the tube. And the result is it's the outside air pushing down and ultimately pushing up the column that allows you to drink from the straw. When in fact you are diving, on the left you will notice, a man named Pascal figured this out, when you're diving down at a depth of 20 meters, the pressure acting on all parts of your body is 3 times the atmospheric pressure. So the pressure of the water pushing down on you is going to be equal everywhere. It doesn't just sit on your head. On the right, you'll notice that the water is pushing on you, but it doesn't push on top of your back because there is no water on top of it. How do we measure pressure? At sea level, it's 101.3 kPa. It's also 760 millimeters, 760 torr, 1 atm, 29.9 inches in mercury, 14.7 or 14.6 pounds per square inch. When we run the calculations in the unit, we will always use atms. So here are your conversions. You'll need to be able to work with all of these. Although I will provide this with you, you must be able to work through the different relationships, so you always are working with 1 atm. Let's take a look at this conversion. If the atmospheric pressure is 638 torr, what is the pressure in the atmosphere? 1 atm is 760 millimeters of mercury, which is also the same as 760 torr. These are your unit relationships or unit ratios. So if we have 638 torr, 760 torr is 1 atm, usual dimensional analysis, you get 0.839 or 0.8, should actually be 0.84 ATMs. And these are conversions you're going to be asked to do on these problems, so if you can, be sure to be familiar yourself with these. Now, what are the relationships here? Well, if you cause the volume, which is 1 liter, to become 0.5 liters, you'll notice the gauge, the pressure increases. Now, from our experience, we know this to be true. So as the volume gets less, the pressure gets more. What about volume and temperature? If you have a balloon in ice water, the gases in the balloon move slowly, and therefore you will see the balloon shrink because the collision on the inside surface of the balloon is not as great. If you place the balloon in boiling water, you increase the speed of motion of the gases, and the result is you see an expansion of the balloon as the temperature goes up. So what happens is, as temperature rises, volume rises if the container can change its size. Now, what about pressure? Well, there's a relationship here. If you have a closed container that has gas in it, and that closed container is cold, then the movement of the gases is slow, and that slow movement creates slow collisions or low collisions with the container walls, and then the pressure's low. If you increase the temperature of the gas, you increase the collisions that are taking place on the inside, and the result is the pressure goes up because the collisions on the surface gets greater. So low temperature means low pressure, high temperature means high pressure. Now, what's the relationship between the amount of gas and pressure? Well, if you have a closed container and the amount of gas inside it is very little, then the amount of collision at any given point inside that container is low. If you cram a whole bunch of gas inside the container, if you increase the mole count inside the container, you have a lot more collisions taking place, and the result is the pressure increases. So as the amount of gas increases, the amount of pressure increases. Remember, we're talking about a container that is rigid, and that means when you see the word rigid, it means the volume is being held constant. So, how do the gas laws fit in on that? Well, there was a series of scientists who studied the variables we just mentioned: pressure, volume, temperature, and how they interrelate. Then what happens is they were able to unify these laws into a single equation. All of these guys were studying a single gas, say oxygen or chlorine, and they monitored the interrelationship of 4 ideas. The ideas of pressure, volume, temperature, and the number of moles or the amount of gas. And they were able to create relationships among them and mathematize them. There is something called the ideal gas law, in which you have a single gas and you don't change things around. A man named Dalton, who actually studied mixing of gases, and finding as Graham's law that studied the diffusion rates. What we're going to do now is work our way through these gas laws.